Let's move on to lecture 9 about seed exercise part. And I prepared group discussion. Unfortunately, we don't have much time today, but definitely we can finish seed exercise 5 today. So please have this group discussion for 10 minutes until 9:50 about your previous seed exercise 6. All right, so sorry for interrupt. I think we may need to speed up a little bit about our discussion session. So for who will be the number 2? Can you briefly?
Things that are quite straightforward, then finding the right models for that top generation when that was over, it was quite straightforward. One thing was that first, I guess everybody picked 2 large capacitors for the getter, and because of the minimal size transistors, the driving strength of the transistors went enough, and that distorted the output. Choosing lower capacitance values, so that for
Okay. So
that, yes, there are many.
Okay. Yeah, it looks very nice. Yeah, it was intentionally designed to check theoretical response when we set the cutoff frequency over the sampling frequency. Of course, that goes to a bit ridiculous capacitance, but it was on purposely. Thank you. Set. And who is number 4 here?
Straightforward. Maybe there was a little struggle in Aalto with the simulation settings for Tran, and then there was like a longer simulating time.
Okay.
Yes, we also in the first case 2 big capacitors, and then I think it's good to learn from that. It's better to assume that theory is right instead of having even the Tran gain would be like 0.5 or 0.6 or something.
Okay.
So then everyone's ready for it.
Okay. Yeah, sounds nice. Yeah, thank you. So during the CAD session, please ask questions to TA. So TA is also Jaehan knows how to run the simulation, so please ask. And who is number 2 in this group? Yeah, 2. Yeah.
2.
I clicked twice by mistake, but it was 2 previously. Okay, how about you? So from my side, 1, 2, 3, 4.
Okay.
Can you briefly just summarize or just briefly say your opinion?
Like member met some problems when they did a PSS simulation.
Okay.
They got one figure, and I think this part is okay for me. Actually, I took a bit of much time to set up the PAC and PSS.
Okay.
I'm not very familiar with that, but after I turned 5 with my circuit, and I think I got right result after that. I think it's meaningful.
Okay, great. Okay, as the
To supplement that, we have 3 different final results. In our group.
Okay, yeah, please discuss with TA which one is most closest to the theory or the answer sheet, and who can share it? The summary. Okay, thank you. Yeah, probably next time both of you can merge into other groups for further fruitful discussion, various discussions. Okay, thank you. So Was everything clear about the purpose of the PSS PAC simulation to see as we increase the cutoff frequency that it approaches to the ideal curve of sample and hold operation? Was it apparent? Okay, yeah, good. Then that was the core intention of the CAD exercise 6. Sorry about this. We could not, we will not be able to cover CD6, but at least we can finalize CD5. So this was a previous simulation situation last week. So let me see. CD5. So simulation DC input range where the gain remains acceptable, no or lower than -3 dB. And we have seen this kind of plot during our lecture today, right? Construct the PAC gain versus input DC voltage graph using Python or Batrap is fine. And identify where is the maximum value it can achieve -3 dB maximum gain. So I also tried to automatically plot this kind of waveform, not the waveform, it's this kind of plot within the virtuoso only, but it was not feasible in my case. So I specifically mentioned execute sequentially by sweeping input DC voltage. So discussion was already done, right, during our lecture today. So it experiences lower current that goes to using Ohm's law. It can be easily predictable that our own switch is bearing. So let me see. Let me bring this waveform. So we can run this simulation again. The PAC result, dB20, then we can plot output, and definitely this one will match very nicely to the theoretical prediction. And the simulation time was slow because I put a lot of points here, 1000 points. So this was intended to approximate this waveform as much as possible. So you can have a see type point. There are so many points. So we don't want to do this for running DC gain here. This is what we want to achieve. So we don't want to run this much of simulation. So we can set 1 megahertz only. And let's set automatic here. And let me send to ADE. And let's run it again. Then it's much faster. Okay, so then for the calculator, we can go here, clip. So clip is limiting the range of this waveform. So for example, if we limit from 1K to 2K, click here and plot, then you can see that this yellow line is only collected for 1K to 2K. And there are several points here. And you can do this way. I mean, of course, you can do manually pick up by drawing the spatial marker and then read the value. But in my case, let me go more easier checking. So we can take average of this 5 points of 1K to 2K range. Then this is the result. If you double click this one, then expression appears again. If you click this one, then you can export the expression to the output side. Let me delete this one. So this is a DC gain. And for the 0.5 volt, let me see. So CAD Okay. Let me just, no. CAD5 DC, let's say. And let me only copy and paste this one. And we don't want the other part. So for 0.5, the value is, click this one again. Yeah, 4.13 milli. 4.13 milli. And you can collect this way of simulation by running it multiple times. Parametric sweep, 3DC, 6 to 0.9. Let's run it for 10 steps, maybe. And there are some values here. So this one is, let me see. Yeah, it becomes a bit tricky when you run the PAC simulation. So at 0.9 volts is minus 18 dB. 0.9 volts, 18 dB. Oh, sorry, 9, 18. Remove it. At 0.86 volt, 86 volt, it goes to minus 10. I'm just roughly copy and pasting to get rough estimation of what is the maximum range of our DC input. So for this one is 8.3. 4.8. For 0.8 volt, it goes to minus 1.56, 67. Minus 0.362. So let's just leave it here because our target was identifying 3 dB location. So here, and let me read the data. In this case, 5 DC, we're testing it. Okay, runs correctly, and we don't want to put like 2 plot. So let me just bring it from other C data size here. So plot, in this case, you have 0, you have 1. Let's have a check. Oh. Okay, yeah, this kind of plot is shown. Let me a little bit do some touch. Okay. So we don't need its limit, its label. So axis is DC input volt and DC gain dB. And let's assume anything else is okay. Then it looks like this. Let me see. What is wrong with this? Oh, should be minus. Okay, then you can see that there is some moment, some moments that experiences minus 3 dB right here. So you can run multiple times more finer data points. For example, here in this case, we collected only data points at 0.8 volt, 0.83 volt, and so on and so forth. So if you want to identify what is the voltage here, you can either use interpolation function within MATLAB or Python, or you can, yeah. Okay. Oh, that's good. So harmonic in this graph, and then at the bottom. Okay. Okay. Right click. This one. Okay. Oh, thank you. Thank you. You proved I was unexperienced. Thank you. Yeah, this is very nice. I didn't know. Okay. Yeah, this will be super helpful in next year's CAD exercise or our lecture. Yeah, this is very nice. Okay, yeah, you can also run this way. Yeah, so like using parametric analysis, for example, running here 20 point. Oh, unfortunately, I am running out of all Swiss chocolate. I can only give you the cookie from London Heathrow Airport. Yeah, thank you. Okay, swap. Very nice. Okay, then yeah, we identified again. I mean, already. So at 0.82 volt, then it experiences minus 3 dB compression or, minus 3 dB attenuation. So you can verify your goal for CAD exercise 7 is verifying improvement over this range. So for example, if you run the bootstrapped sampling switch, it will be like this. This is expected result. So yeah, so thank you for attending this lecture today, and we will have a short break for 5 minutes, and we will go quiz.